All right, howdy folks. Today let's look at section 2.3, which is solving, again, first order, but these are called homogeneous equations, okay? Solving first order homogeneous equations, and for that I need to define as to what a homogeneous function is, and then define what a first order homogeneous equation is. So that's the order in which we're going to look at this, okay? All right, a function f is said to be nth degree homogeneous if this happens. F of tx comma ty is t to the n times f of x comma y. I lied here. N need not be a natural number. N needs to be a real number. Sorry, could you fix that, please? One second. Can I fix it right in front of you? Let's see. There we go. That's fixed. So n, that n needs to be just any real number. Okay, cool. So with that, let's look at that. F of tx comma ty, you should be able to express that as t to the n times f of xy. I don't know if it makes sense to you or not, but with a few examples, I'm sure it will. Okay, but as a challenge, can I ask you this? Determine if the function is homogeneous, and if yes, state the degree of homogeneity. F of xy. I give you something like that. I'm asking you, hey, is this a homogeneous function? If yes, then what is its degree? Just looking at the definition, would you know exactly what the procedure ought to be? Can anybody think of that? Right? When you take a few upper level math courses, stuff like this is just like piece of cake. I'm sure even now, to a lot of you, it's crystal clear as to what it is that you need to do. What is it? Would you agree the definition says everything hinges on figuring out f of tx comma ty and checking whether or not that is equal to t to the n times f of xy. Do we know f of xy? Yep, this stuff. F of xy square root of x plus y times 4x plus 3y. Will that allow us to figure out f of tx comma ty? I don't know, man. Okay, you do. Why do I say that? Now if I asked you this, if f of xy is equal to this, can you tell me what is f of 2 comma 3 is? You don't need to have taken calculus 3 to be able to answer this question, I take it. F of 2 comma 3, what would you do? I don't care about the final answer. What I care about is, what do you do when I ask that? Simple, man. I'll plug 2 for x and 3 for y. Yes, you are absolutely right. Right? And if that is the case, if I say, can you find f of p comma q, what would you do? I'll do the same thing, man. I'll plug p for x and q for y. Yep, you're right. So is it any difficult to figure out f of tx comma ty? Wherever you see x, you plug in tx, and wherever you see y, you plug in ty. Right? As simple as that. And then after you do that, you ask, whatever is the resulting expression, can I express it in terms of t to the n times f of xy? That's the key. Cool? So, f of xy equals square root of x plus y times 4x plus 3y, and f of tx comma ty, just as promised, replaced x with a tx and y with a ty. And so we have a 4tx plus 3ty. to square root of tx plus ty times this thing. Now let's see. Can we factor out a square root of t from the radical thing? Yep. Can we factor out a t from the stuff inside the parenthesis? So we could factor out a square root of t from there and a t from here. Would you agree that gives us t square root of t times square root of x plus y times 4x plus 3y? Now, t square root of t. Can we write that in a slightly different way? T to the n? Yeah, that's same thing as t times t to the 1/2. So t to the 1 plus 1/2 or t to the 3/2. So that t square root of t can be written as t to the 3/2. Okay, what about the rest? Is this stuff, square root of x plus y, is that related to f of xy? Of course it is. It is exactly f of xy. So guess what? We could write this as t to the 3/2 times f of xy. Now, this is why putting equal signs is very, very important. We have now shown that f of tx comma ty is equal to t to the 3/2 f of xy. Does that satisfy this condition? F of tx comma ty should be in the form of t to the n f of xy for the function to be homogeneous and of nth degree? Yes, it does. So what degree homogeneous is this? T to the n. N gives you the degree. Here that n happens to be 3/2. So certainly f is homogeneous. F is a homogeneous function of degree 3/2. Cool? That's the idea. I'll do quite a few problems in this one because some are not as obvious. Okay. There's something else I wanted to cover. What did we find? We found that this is 3/2 degree homogeneous, right? How should I put it? What I'm about to show you, there's a reason for it. So here is the idea. Because we detected that this is 3/2 degree homogeneous, automatically we could do something. We could factor out a x to the 3/2 from this whole expression, or in fact we could factor out a y to the 3/2, which is what I will attempt to show you next. Okay, so if we factor out a x to the 3/2, we can, by in fact factoring out x to the 1/2 from this, we get 1 plus y over x, and x from this, we get 4 plus 3 times y over x. What did I do? I factored out a square root of x from this guy and an x from this parenthesis, and so that gave me this x to the 3/2, which is exactly the same as the degree of homogeneity. Okay, now look at this guy. We have square root of 1 plus y over x, 4 plus 3 times y over x. Could we replace y over x with some u? Yeah. So, this stuff now becomes x to the 3/2 times square root of 1 plus u times 4 plus 3u. What does? Originally, what was a function of x and y, now the y has completely disappeared. It's just expressed in terms of x and a new variable called u. Isn't that interesting? What was originally a function of x and y, this f, now we wrote that as a function of x and a different variable called u. Different in the sense, of course, it is related to y and x. U is y over x, but we can write like that. Okay? Why? What's the purpose of that? Well, it is because in these kind of homogeneous differential equations that we are going to learn about, the original equation will not be cannot be solved using separation of variables. However, if you convert to this x's and u's, it is separable, and so we can solve. Okay, if you didn't get that, don't worry too much about it. What I'm saying is, what are called homogeneous differential equations, first order, we want to solve them by using separation of variables, which is a technique that we already learned. But unfortunately, those equations, you cannot separate them into x's and y's. However, if they happen to be homogeneous, you can replace that equation in terms of x and y to terms of x and u, and in that it is separable. Look at how clever mathematicians are. Okay, that's the idea. And there's one more point that I want to drive at. So this stuff is x to the 3/2 times f of what? Does the question even make sense to you? X to the 3/2 times f of what? What do you mean? Well, look at this. Let's go back to the original f. The original f is in terms of x and y. Cool? And is given by square root of x plus y times 4x plus 3y. What I'm asking you is, what should you plug in for x and for y so that this stuff, the right hand side stuff, will give you square root of 1 plus u times 4 plus 3u. Let me repeat that. What should you plug for x and y so that into f of xy, the expression for f of xy, so that you get square root of 1 plus u times 4 plus 3u. Check this out. This is a x, but we have a 1. Maybe, should we plug x equals 1? Right? Instead of x, we'll have a 1. Okay, and here we have a y, but here we have a u. For y, should we plug in a u? Well, at least that would definitely satisfy this part of it. 1 for x gives you 1 plus u. 1 plus square root of 1 plus u. That's what this is. But the only thing is, would that satisfy this as well? Well, 4 times 1 is 4. That is 4. Plus 3 times u. This is 3u. Yep. So if we say f of 1 comma u, then this can be replaced by f of 1 comma u. Okay. That's the point I'm trying to drive at. The original f of x comma y can be separated as x to the 3/2 times some function of u. Now I can say, because 1 is a constant, I can say this is equal to some g of u. Folks, if you understood that, that's fine. If you didn't understand, don't worry too much about it, okay? All right. This kind of a manipulation, especially, I teach this for the sake of math majors especially. They are expected to learn these kinds of manipulations because tomorrow they're going to prove, tomorrow meaning in one of their classes, they will need to use these kind of manipulations to prove certain things. Okay? But as engineers, if you don't, that's fine. So like I said, we could have factored it y to the 3/2 and we get this stuff, and the idea there being, you can write this way. Okay, don't worry too much about it. Let me move on to asking this question. Is this function homogeneous, and if so, of what degree? What did we say? How do you go about doing this? Figure out f of tx comma ty. So let's do that. If f of xy is this, f of tx comma ty, replace x with a tx and y with a ty. So we do this. Can we factor out a t from the bottom? Yup. Would that t and this t cancel? And so would we get sine of x over x plus y? Yep. Okay. Is this related to f of xy? Can we write this in terms as t to the n times f of xy? Hey, wait a minute. This is just f of xy. F of tx comma ty equals f of xy. There is no t to the n. Or is there? Can you write f of xy as some kind of a t to the n f of xy? Yep. Couldn't we write this as t to the 0 times f of xy? T to the 0 is 1, provided t is not equal to 0. That's a simple assumption that we could make, because it wouldn't make any sense to say f of tx comma ty if t happens to be 0. You're just talking about f of 0 comma 0, a special case. So that's a trivial case. So to avoid the triviality, t cannot be 0. So yeah, this is in fact homogeneous and of 0 degree. Oh, okay. By the way, one more thing I wanted to tell you. This is, look at the spelling of this one. Homogeneous. There is a neous. There is another word which is homogeneous. There is no e. This e is missing in that. That should be pronounced as homogeneous, which is used, that word is used in along with mixture. This is a homogeneous mixture. So we are not, this is not homogeneous, this is homogeneous. Okay? It's not like somehow I'm a stupid foreigner guy who doesn't know English, and so I'm just saying homogeneous when I'm supposed to say homogeneous. No. I am a stupid foreigner guy, I agree with that. But on this one, I'm not, at least. Okay? That's a joke, man. Come on. So this is a homogeneous function of degree 0. Let's move on. I like these. Is this homogeneous? So what are we supposed to do? Or did I do that? Let me first, I think I may have done something to it, so I don't want to show you what I did before I attempted it. So what's the process? You figure out f of tx comma ty. Okay, and which would be natural log of the quantity tx cubed over natural log of the quantity ty cubed. What do we do? Oh, can we cancel the natural logs? Big time no. Right? Don't ever do that. Oh, wait a minute. I got it, man. That's the same thing as natural log of x cube minus y cube. Natural log of the quantity x cube minus y cube. No. What? Yeah, come on. Isn't natural log of a over natural log of b equal to natural log of a minus b? No, it's not. Oh, come on. I swear, I know there's something just like that. Yep, I know what you're talking about. What you are talking about is natural log of a over b equals natural log of a minus natural log of b. Is this in that pattern? Nope, it's not. We have natural log of a over natural log of b. Right? So, nope. We cannot write like that. Ah, got it. I'm going to raise both the top and the bottom to a power of e. Right? Wow. What a clever guy I am, right? I'm going to raise both the top and the bottom to a power of e. Big blunder. What? Yup, you cannot do that. Why not? Well, here is the idea. If you have natural log of x equals natural log of y, then if you said, well, I'm going to raise both sides to a power of e, that's okay. Which in turn gives you x equals y. Nothing wrong with this guy. Yeah, but that's the same thing. No, it's not the same thing. What you're saying is something tantamount to this. If I have a over b, can I square both the top and the bottom? No. The reason people think it's perfectly all right to do that is because of this. Because people do not put equal signs where they belong. Whether you are claiming it or not, when you say, I'm going to raise both the top and I'm going to square both the top and the bottom, then you are actually implicitly, though not explicitly, saying that I'm going to set this equal to whatever I get if I square both the top and the bottom. Right? But that's not equal. A over b is not equal to a square over b square. Right? If that were to be true, then your friend could borrow $10 from you, which is 10 over 1, and you say, hey dude, a over b is the same as a square over b square, so give me 10 square over 1 square dollars back with 10 square, and which is $100 back. Right? So that doesn't work. Okay. So let's continue with this. So what do we do? Hey, wait, there is a property of logarithms. What? Like that power, that exponent, will become the coefficient. Can I say natural log of x cubed is the same as 3 times natural log of x? Now you're like, damn man, I'm going to shut up. Because if I say, yep, you can, then you're going to say big time not equal to or something like that and insult me. Nah, I won't. That is correct. Right? And so we can cancel the 3's or they divide into 1. And so we get natural log of x over natural log of y. So natural log of x cubed over natural log of y cubed is exactly the same as natural log of x over natural log of y. Isn't that interesting? Okay, but we got to talk about f of tx comma ty. So that's going to be natural log of tx over natural log of ty. Cool. Can we cancel the t's? No. You cannot. Can you raise both the top and the bottom to the power of e? No, you cannot. Can I write this as natural log of tx minus ty? Natural log of the quantity tx minus ty? No, you cannot. Damn. What do I do? Wait. I can write this as natural log of t plus natural log of x over natural log of t plus natural log of y. Can I do that? Yes, you can. Okay. So what? You're going to write this as natural log of t plus natural log of x. Great. Over natural log of t plus natural log of y. Wonderful. Okay, now where do we go from there? Oh, can we cancel natural log of t from? No, you cannot do that. Damn. Okay. Guess what? There's nothing you can do. So, the function is not homogeneous. I remember. Every time I show this, there's a big sigh from the whole class. It's such a fun thing to experience. No. This is not a homogeneous function. Did I say the function has to be homogeneous? Nope, I didn't. I asked whether this was homogeneous or not. If yes, what degree? Right? Cool. Okay. Now, definition. A first order ODE of the form m of xy dx plus n of xy dy equal to 0 is said to be homogeneous if both m and n are homogeneous functions of the same degree. Let's see if we can make sense of it. We must have a first order differential equation, and that we need to write as, right, we can manipulate and write this way: m of xy dx plus n of xy dy equal to 0. Sometimes the problem is given in this fashion, and some other times when it's not, it's given in the form of dy dx equals some f of xy. We can manipulate that and write it this way. Okay. And when you do that, if it turns out this m and n are homogeneous functions, not only that, they must be homogeneous functions of the same degree. In that case, we will call this first order equation as a homogeneous equation. And why do we care about that? We care about it because there is a certain standard procedure that you could now adopt the moment you recognize it is a first order homogeneous equation. And what is the procedure? The procedure is, if it turns out that m of xy is simpler, whatever that means, then n of xy, we substitute x equals vy and dx equals, where did we get this from? Product rule, right? If x equals vy, dx is going to be v dy, first function times the derivative of the second function. Here we don't have a derivative, but we just have a differential, plus y dv. Okay. So x equals vy and dx equals v dy plus y dv. And then here is what happens. When you do that, the resulting equation will be separable. And we can use the separation of variables method that we learned in 2.2. That's the idea. Or if n is simpler, then the substitution you make would be y equals ux and dy equals u dx plus x du. And then use separation of variables. Cool? I'll show you quite a few examples. Show that the differential equation is homogeneous and then solve. Does this have the form of m of xy dx plus n of xy dy equals 0? Yes, it does. Cool. Can you tell me what m of xy is? Whatever dx is being multiplied by. So m of xy is x plus y. N of xy is whatever dy is multiplying. Dy is being multiplied by x. So n of xy is x. So m of xy is x plus y and n of xy equals x. Can you figure out if these are homogeneous? Piece of cake. M of tx comma ty is t times m of xy. So first degree homogeneous. N of xy is tx. N of tx comma ty is tx, which is t times n of xy. And so that's first degree homogeneous. So both m and n are homogeneous functions of degree 1. Right? And so the whole differential equation is homogeneous, first order homogeneous. Okay. Now how do we apparently solve these kinds of problems? We make a substitution, either x equals vy or y equals ux. Right? That's what previous slide I talked about. And which substitution to make depended on what? Whether m is simpler than n or the other way. Between x plus y being m and n being x, which one is simpler relatively? X. It's just an x. Whereas this is not that much more complicated. It's just x plus y. Yeah, n of xy is x. That's a simple one. So the procedure said, in that case, plug y equals ux and dy equals u dx plus x du. Right? Since n is simpler, plug y equals ux and dy equals u dx plus x du. So let's do that. So let's plug x plus ux dx, x plus, for y I plugged in ux, times dx, plus x times, for dy, I went to the original differential equations, folks, and that's where I'm plugging all these things. For dy, I plugged in u dx plus x du, and that's equal to 0. Now let's just multiply out, and we notice that we get a x plus, there is a ux dx, and there is a xu dx. So I brought all the terms that have a dx in it together, and so we get x plus 2ux dx. And then there is x times x du is x squared du. Right? If you don't believe me, just pause this video and check to see if what I got is right. And convince yourself. So that's what this reduces to. But then, wait, couldn't we factor out an x from these two terms? And when we do, we get x times 1 plus 2u times dx. And then this is, then can we not divide by x? We factor out an x, or think of it this way. Let's divide throughout by x. Wouldn't this reduce to 1 plus 2u dx x du equals 0? Am I allowed to divide by x like that? Am I allowed to divide by x on both sides? If I have an equation, am I allowed to divide both sides of the equation by whatever I want? Well, what if x is 0? Can I divide both sides by 0? That's a no-no. But let's ask, could x be 0 in this case? What happens if x is 0? We have y equals u times 0, so y would be 0. X is 0, y is automatically 0. That's a trivial solution. So we are guaranteed that x will never be 0. Or another way of looking at it is, what would dy dx equal? Dy dx would be negative of x plus y over x. We would have an x in the denominator. Can x be 0? No. So that's the idea. So anyway, and we got this. Okay, what do we do now? Can we use separation of variables? Can we separate the u's and x's? Yep. 1 over 1 plus 2u equals negative 1 over integral, negative integral 1 over x dx when you separate. And you can integrate them. Okay. And since I have covered integration, and this is all simple integration, I won't spend too much time. But what is absolutely essential that you understand is, why did we resort to all of this? We did because the original equation cannot be separated. You couldn't use separation of variables technique to solve this one, right? Because there is a x dx and a y dx and a x dy. I don't think you can. Nope, you cannot. Okay. That's why we recognize it to be a homogeneous equation, and then we apply the procedure that is suitable for that problem. Cool. And then once you get to this stage, just replace u with the original equation is in terms of x and y, so we cannot leave it in terms of u. But notice y equals ux, so u must be y over x. So go ahead and make that substitution. You're done. Cool. That's the idea. Let's move on to this one. What is m of xy? Be careful. M of xy is negative y. N of xy, x plus square root of xy. Okay. I don't know if yeah. I think I left it for you guys to establish that this is in fact a homogeneous equation. Okay, I didn't do that part. So we do this, and now since m is simpler, because m is just simply negative y, we'll plug in x equals vy and dx equals vdy plus y dv. Cool. And when we do, we get this, and I just multiplied everything out, and then I noticed that there is a negative vy dy and there's a positive vy dy. They add up to 0, and then you separate and divide throughout by y, and manipulations like that. I'm giving you this integral, which is straightforward to integrate. Both sides are straightforward to integrate, and that's it. There's nothing to it. Cool. All right, next, let's see. Ooh. Yeah, look at this one. This one is not in that form of m of xy dx plus n of xy dy equals 0 to begin with. So we got a bit of work to do. So which is, first be sure to write this in the sense multiply throughout by dx, or add y to both sides and then multiply by dx and then subtract and blah blah blah. Okay, I'll leave it for you to see how this equation could be manipulated to look like this. I'll leave it to you. Now, what is m of xy? Coefficient of dx. What's n of xy? Coefficient of dy. So we get plugging, because clearly the n is simpler, just a negative x, whereas m is much more complicated. So we do this y equals ux and dy equals udx plus x du, and that's what I'm plugging. And notice if we multiply, would we get a ux dx? And then you have a minus ux dx. And so they add up to 0. I should have recognized that right there. I didn't. Yeah, no. As an afterthought, I recognized it. I'm an idiot, man. Okay, so square root of 1 plus u square dx, and separates like this. I like this integral. How do we integrate 1 over square root of 1 plus u square du? Well, this is where you need to use trig substitution. So please watch the video on trig substitution, and this will become piece of cake. But I think, the nice guy that I am going to discuss that here. Here is the idea. Draw yourself a right triangle. Okay. Whenever you see something like a square root of a square plus x square, or a square plus u square here, or a square minus square root of a square minus u square, square root of u square minus a square, any of those three things, you draw yourself a right triangle first. And then one of the sides is going to be 1, a second side is going to be u, and the third side is going to be square root of 1 plus u square. Okay. Now, obviously the biggest one should be the hypotenuse. Of the three quantities, 1, u, and square root of 1 plus u square, which one is the biggest? Square root of 1 plus u square, right? That's got to be bigger than 1. That's got to be bigger than u. And so, clearly, square root of 1 plus u square is the hypotenuse. And one of the sides should be 1 and the other side should be u. And I typically pick the vertical one to be u and this to be the constant. And then we need to label one of these angles with a theta. It doesn't matter, if you were to switch this to 1, make this vertical one as a 1 and this is a u, and also if you feel like making this other angle, this other acute angle as theta, the only thing is don't make the right angle into theta, but if you pick any other one of them and call them as theta, this procedure works. Okay, now first you need to figure out the ratio u over 1. Always it's that over the constant, u over 1. What is that in terms of theta? In a right triangle, if this angle is theta, isn't u the opposite side of theta and 1 the adjacent side of theta? So the ratio u over 1 is automatically opposite over adjacent, which is nothing but tangent theta. Cool. So tangent theta is u over 1, or u equals tangent theta. And immediately figure out what du is. Du is secant square theta d theta. Cool. What did I do? I formed a ratio u over 1 and asked what trig function is that. And that turns out to be opposite over adjacent tangent. Similarly, form the ratio square root of 1 plus u square over 1. And that's going to be hypotenuse over adjacent. Hypotenuse over adjacent. We know adjacent over hypotenuse is cosine. Oh, so this must be the reciprocal of that. So square root of 1 plus u square is secant theta. Cool. All right. So we have u to be tangent theta, du to be that, and we have this. We are ready to solve the integral. 1 over square root of 1 plus u square, plug in a secant theta. And for du, plug secant square theta d theta. And on the right hand side, of course, natural log of absolute value of x. And this reduces to integral of secant theta d theta. But integral of secant theta is natural log of absolute value of secant theta plus tangent theta. But these are in terms of theta. We want in terms of u. In fact, we want in terms of x and y. So, as a first step, what is secant theta? Hey, secant theta is square root of 1 plus u square. What is tangent theta? U. Well, if these things were not to be here, or let's say the answer came out to be natural log of sine theta plus cosine theta. Can we figure out what sine theta is? Yeah, we have the triangle here. So u over square root of 1 plus u square, opposite over hypotenuse. That's it. So that's the beauty of this triangle. It will allow us to figure out all the trig functions. So we got square root of 1 plus u square for secant theta, that. And then plug back u equals y over x, and you're done. Cool? It's a very nice problem. All right. dy dx. I like this one. I'm going to try something slightly different. Instead of writing this as m of xy and all that stuff, and instead of plugging y equals ux, because I see a y over x, isn't this the same thing? Y over x is u. So for y over x, can I not just simply say u? And so wouldn't the right hand side be u natural log of u? Right? Look at how simple that is. The right hand side is simply u natural log of u, end of the story. The only question is the left hand side. That cannot be dy dx. Y's should disappear. We must have everything in terms of just u and x only. Okay, but we have dy dx. What do we do with that? Check this out. If y equals ux, to find dy dx, can I differentiate both sides with respect to x? When I do, the left-hand side, ddx of y, that's dy dx. And the right-hand side, ddx of ux, u times x. ddx of u times x. What's the big deal about differentiating that? Apply product rule. So u times the first function u times the derivative of the second function with respect to x, ddx of x, is 1. So we get u plus u times 1 plus x times ddx of u, which is du dx. So by applying a simple product rule, we can say dy dx is equal to u times 1, which is u, plus x times du dx. End of the story. So what are we supposed to do? We are supposed to replace this dy dx with a u plus x du dx. Cool? That's another way. And for some of these problems, in fact, that seems like a much better way. So dy dx we'll replace by a u plus x du dx, and like I said, the right hand side is u natural log of u. And now separation of variables, du over u times natural log of u minus 1 equals dx over x, and integrate both sides. Whoa, Nelly. How do you integrate du over u times natural log of u minus 1? Well, can we do substitution? W equals natural log of u minus 1, right? Because dw would be 1 over u du. There is a 1 over u du in the integral. So look at me. I didn't even bother to do that. I just did it in my head. And yeah, but you are smart people. W equals natural log of u minus 1, folks. So that means dw is 1 over u du. So this whole thing becomes dw over w. Isn't that natural log of absolute value of w? That's what I wrote here. Cool? If you want to actually scribble that part, please be my guest. That's all I did. By substitution, w equals natural log of u minus 1, I got this one. And just plug back, you're done. Next. X square e raised to negative x. I like this problem. Here, once again, I'm looking at that y over x. That's what I'm tempted by. Because I'm seeing a y over x occurring naturally, I'm saying, can I do that? Just write everything as in terms of y over x. Wait. So you mean we should not have an x square? Okay. What if we divided both sides by an x square? What happens? X square over x square is just 1, and we will have a e to the negative y over x, plus we'll have a y square over x square, which we can write as y over x, the quantity square. And on the right hand side, we have xy divided by x square. That reduces to y over x. So this is dang, I could have done that, or that's okay. What I said is okay, but looks like what I did instead is I divided throughout by xy. Ain't that clever? X square over xy becomes x over y. Y square over xy becomes y over x, and that's equal to dy dx. Okay, now if y over x is u, x over y is 1 over u, right? And so we'll plug in y over x equals u, and this reduces to 1 over u e to the negative u plus u equals, and for dy dx we'll plug in this, and quite nicely u's cancel, and we get a simpler integral. And this is integration by parts. We're done. If this appears to be complicated to you and you just want to, no man, I'm more comfortable with m dx, m of xy dx plus n of xy dy, and doing that, yeah, you can do that. Okay? All right. So this is straightforward. Why does this work? This is what I was trying to show you. Because we can, these are nth degree homogeneous functions. If you want to tune out at this part, especially if you're engineering majors and you don't care about these kind of theoretical stuff, don't worry about it. You can stop the video right here. But for the math people, this is the idea. Why does this work? That's because when m is nth degree homogeneous, we can write that as x to the n times m of 1 comma u. Similarly, n of xy can be written as x to the n times n of 1 comma u, and dy of course is u dx plus x du. Now I can divide throughout by x to the n, and so that disappears. X is not equal to 0, so we are okay, we can do that. And m of 1 comma u is nothing but some function of u, so I called it as f of u. Similarly, n of 1 comma u is some function of u, so I called it g of u. Now the question is this resulting equation, is it possible to express it as separation of variables? Yep, notice there is a f of u dx and a g of u times g of u dx. So we can factor out a dx and group them together like this. And then we have x g of u du equals 0. And now we are in a perfectly wonderful position of separating them, and we can integrate. That's why this works. Amigos, adios.